All right. So if you guys want to take a look at your notes here, notice that for 3.8 here, this first page is very conceptual, and I think it's helpful, but I think it's more helpful if we look at the tangent graph first. So today what we're looking at is the tangent function. We already touched base on that during 3.2. The kind of key thing here at the top we can talk about, and then I just want to go right to the graph and then come back to kind of this conceptual, the conceptual ideas. Yeah. So tangent is equal to sine over cosine. Um, and what this really is it's our slope of the terminal side here. So as I'm looking at that, if I, thought about counting slope here, I start at 0, 0. I'm going to go up and over, right? I'm going up a y amount, which is the same thing as sine, because this point here would be like cosine, sine. And then I'm going to go over the x amount, which is also cosine. So this slope of this line is the same thing as tangent. So here we have three things here: sine over cosine, it's the slope, and y over x. And we're going to use y over x a good amount for that. This is how we're going to think about it. All right, so I want you just to kind of come over to the second page here, and we're going to just go ahead and just look at the tangent graph. So the key thing about this tangent graph is that we have vertical asymptotes on it. We didn't have that sort of thing on sine or cosine. And so I just kind of want to briefly run through why we have these vertical asymptotes. So if I had, this point right here, that would be 1, 0. This point here is 0, 1. And so let's stop here. This is pi over 2 right here. And if I were to find the slope at pi over 2, I would say it's equal to my y over my x. Hold on a second. Where'd my thing go? Oh, did it put it there? No. Shoot. Is that right behind that? Oh, huh? Yeah. Oh, and then how do I stop sharing when I'm done? Okay, I'll come back to it. All right, so our slope here is going to be, hi, y over x, which in this case is going to be 1 over 0. And so we see how that is undefined here. Thank you. Okay, and then we're going to have the same thing at 3 pi over 2, which is down here, because this point is going to be 0, negative 1. So at 3 pi over 2, our slope is going to be negative 1 over 0, which is undefined, right? And that's what's happening on these axes. And we can see a vertical asymptote if we look at it like negative pi over 2. And we're thinking we're going this way, and negative 3 pi over 2 would be up here. All right, the other thing is another key point on this would be 0, our slope of 0. So when we're over here at 0, our slope here would be 0 over 1, which is 0, right? So we're good here at 0. Our slope is going to be 0. All right, so, and then the other one would be, if we look at pi over 4, so here that is the square root of 2 over 2 and the square root of 2 over 2. So if I take, the slope of that, that is just going to be square root of 2 over 2 divided by the square root of 2 over 2, which gives me 1. So I can see right here, this point, when I'm at pi over 4, that slope would be 1. Okay, so that's where we're getting these values, and that's why we have the vertical asymptote. So let's go back to the front page now, and I think that it will make a little bit more sense how they're explaining. So basically they're saying, let's look at the slope of the terminal ray as our angle increases from 0 to pi over 2. So at this point here, our slope is 0. And then I'm just going to kind of assign some potential slope values here. So let's say this is m is equal to 1/2. Let's say this is m is equal to 1. Let's say this is m is equal to 3. Basically, we're just going to keep going, right? Our slope is going to get steeper and steeper and steeper to infinity until we get to an undefined slope, when we actually get to that pi over 2. So that's what this is trying to show here. So as theta approaches pi over 2, the slope gets steeper and steeper, more and more positive. And then when theta equals pi over 2, the terminal ray is now vertical. So the slope of this vertical line is undefined. And we talked about that looking at our ordered pair. M would be equal to 1 over 0, which is undefined. Do you need a pencil? Got one there. All right. So now we can see that when we say the slope is undefined, it is infinite. And as I'm looking over here at my graph at pi over 2, I get, closer and closer to pi over 2. I'm not going to actually, hit it, but it's undefined there at pi over 2. So that's what these circles are trying to show us. Also, if we investigate what happens when we go from pi over 2 to pi, so now we're in quadrant 2, here we're going to have, m is equal to a steep slope here, and it's also negative, right? Because we're going this way with it. And then we could say, for example, this is m is equal to -3, and then m is equal to -1, and m is equal to -1/3. And we're just going to keep going, and that slope is going to become more and more and more negative, out to negative infinity, but not hit 0. And then it transitions from negative infinity to 0 once we get on that axis right here. But here it's just going to keep going to negative infinity till it gets closer and closer and closer. All right, so that's what this meant. I just feel like it would be kind of hard to connect what we're talking about without kind of picturing the graph. Next page here then, they continue with, as we go from pi to 3 pi over 2 now our slopes are positive again. We can see that we have a slope in a positive direction, and they progress from a slope of 0, and then it increases without bound as it approaches 3 pi over 2. All right, so key concept. Each time that the terminal ray is vertical, the slopes are undefined. They approach negative or positive infinity. When we graph the tangent function, this means that we will see vertical asymptotes. That's what goes in here. We will see vertical asymptotes when theta is equal to pi over 2 and 3 pi over 2. And then each half turn around the circle will create another vertical asymptote. And so, each half turn, we can do that to infinity, right? We can just keep on going. And our graph would just keep on going as well. So when we talk about that, where is it? It's down at the bottom here. I'm just going to jump there. So the function y equals theta has vertical asymptotes at pi over 2, and then you add pi as many k times as you want. K is just an integer. So that's how we describe that vertical asymptote is going to be at pi over 2, and then just keep adding pi or subtracting pi an infinite number of times. All right, so that's really the vertical asymptote. Then we also have important features for this graph. Similar to how we did with sine and cosine, we have our A, we have our B, we have our C, and we have our D. So I want to jump over to Desmos so we can kind of look at this and see how it changes when we change that function. One thing to note here is for the period, remember for cosine and for sine, that was 2 pi divided by b. The period on tangent is just pi. And if we look at the cycle here, we're going from negative pi over 2 to pi over 2, which that is pi. And so our period here, one cycle, is going to be pi. So make sure when you're using this formula, you use pi over b, not 2 pi over b, like we did with sine and cosine. All right, so, yeah.
Is that the absolute value?
Mm-hmm. Okay. Yeah. Yeah, because it's describing a distance, like how far you're going in one cycle. Okay, so I want to go to Desmos and let's pull up that graph and then you guys can just look at your notes here. So y is equal to tan x looks like this. So if we change the a value here, so what's sitting out front, let me do another one so we can kind of see the difference. If I do 2 tan of x, what this is doing is it's making it steeper, right? So we have the vertical dilation of the graph is going to be controlled by that a sitting out in front of the tangent. In this case, I put 2. Likewise, if we made that a negative, it's going to reflect it about the x-axis. So when you're doing these problems, you do want to kind of have in your head that when you're tangent and it's positive, it's going to look like this red one. And when it's negative, it's going to look like the blue one, and just be able to identify that with the graph. And then we also have the vertical shift like we did before. So if I say -2, it's moving it to the right 2, just like we did for the other ones. And then we also have a vertical translation. Oh, wait, that's what did I just do? Sorry, I just did a vertical translation. Sorry, hold on. Let me put parentheses around this. So -2, there we go. So that's moving it to the right 2. And then if we add 3 on to the end of it, now we're moving it up. And the place we're going to kind of look to see that it has moved up is we're looking at this curve, like the inflection point. When it changes, it's like concave down and then it becomes concave up right here. That is what moves up here. So that's how you can kind of see your vertical movement, Emily. Thank you. Okay, so that's a vertical translation. And if we change the B in front of that, it's going to change the period. So this is going to, make it tighter. It's going to make it smaller. So anyway, that's a kind of a look at the different tangent functions here. All right, so back to our notes. Now we're going to actually look at some of the problems. Okay, example 1. Says a portion of the function f is shown below. The function f can be written as, here we don't have a c, there's no phase shift on it. We want to figure out what a, b, and d are. So we're going to start with the period because we can use that to figure out what b is. So we're going to say the period here. We're going from -pi/4 to pi/4. And so that means that distance there would be pi/2. And if it's helpful, if you want to just think about, the distance wise, if you're going pi/4 and you're doing another pi/4 segment, that is 2 pi/4, which will get you to that pi/2. So you can write it out like that, or if you just want to think about it, if you had a quarter of something and a quarter of something and you added them together, it would give you a half. All right, now we're going to use our formula that says period is equal to pi/b. And we are going to put in the period, which is pi/2, set it equal to pi/b, and that means that b is equal to 2. All right. The a, so there's no amplitude on tangent because there's no max and there's no min. But the a, we're just going to think about in regards to our parent function. So when we have a 1 right here, that is going to be like a 1 sitting in front of the tangent x. That's what the parent function looks like. So this would be a is equal to 1, and that's what your tangent graph is going to, look like when a is 1. And then also we have a midline, which is going to be kind of that key inflection point where we're, changing from concave down to concave up. And so for this one, our d is just equal to 0. All right, and that's it for that problem. The next one, it's asking what the period is, and we know what b is here. B is going to be 2. So if b is equal to 2, then we're going to say the period is equal to pi over b, which is equal to pi over 2, which means that that is the period. All right, next one is a different kind of problem. So this one says let g be the function defined by, and then we have a tangent function here. Which of the following gives the vertical asymptotes to the graph of g? So if we think about our regular parent function, at g of x, we have tangent, and when tangent is pi over 2, that is where we have a vertical asymptote. So I'm just going to make a note here. G of x equals tangent pi over 2 is a vertical asymptote. So we have a different vertical asymptote with this problem here, where we've got x over 3. So we need to figure out where's the vertical asymptote on this problem. So we are going to set pi over 2 equal to pi over 3 to see what that means for x. What does x need to be to create another vertical asymptote at a place that's not pi over 2? So we're going to say x over 3 is equal to, and we know it's equal to pi over 2, but not just pi over 2, plus pi times k, because we have those pi increments that we're going to continue to just have one vertical asymptote after another. And then at this point, I want to solve for x. So if I want to get x by itself on the left side, I'm going to multiply the left side by 3, and I'll also multiply the right side by 3. And when I do that, on the left, the 3 divided by 3 is 1, so that gives me x. And then I'm going to distribute this 3 to both of the things in parentheses here. So this becomes 3 pi over 2 plus 3 pi k. All right, and so our answer here will be C. This is where the vertical asymptotes will be for this function here. All right, so you'll get quite a few practice problems on that kind of problem on your homework. Okay, example 4. A portion of the function k is shown below. Which of the following could be the expression for k? So we're going to start by trying to get that b value. So we can look at the graph, and we can see that the period goes from negative pi to pi. So that means if it goes from negative pi to 0 and 0 to pi, that's 2 pi worth of distance for that cycle here, from looking negative pi to pi. And then I'm going to go ahead and set that equal to our little formula, pi over b. I'm going to cross multiply here. So that gives me 2 pi b is equal to pi. B is equal to pi divided by 2 pi, which means that b is equal to 1/2. Okay, so that's the b. And then as we're looking here on our graph, we're going to go ahead and put our midline in. So that's the place where that inflection point is happening. We're changing from concave down to concave up. So that means that our d is equal to -2, because that was our vertical translation down. So as I'm looking at my answer choices, I see A and C are my only two options with that midline. And then A is going to be it because, 1/2 times x is the same thing as x over 2. So that would be A. All right, number 5. All right, we have the graph of G's given. We want to figure out where A and B are constants here, what they would be. So I'm again going to start with the period here. I see that this is going from -4 pi over to 4 pi. That's one cycle, which means that period would be 8 pi. And then I want to set the 8 pi equal to pi over b. I'm going to cross multiply. 8 pi b is equal to pi. B is equal to pi over 8 pi, which means that b is equal to 1/8. And I see in my answer choices, my option is it's either less than 1 or greater than 1. So 1/8 would be less than 1. So I know that B is less than 1. And then as I'm looking at the graph, I just need to decide, is A positive or negative? Well, remember that if it was positive, it would be, going in this direction here, something like this. So this one is going to be negative. So that means, and I'm just going to write A is negative. I'm going to erase my little thing here because we're just looking at that graph. A is negative because it's reflected over the x-axis. And so we're going to choose D because A is less than 0 and B is less than 1. Okay, for C, we have we have a B and a C that we're looking for here. So notice here that our graph has shifted. Usually this little inflection point is sitting on 0 for tangent, and now it's sitting on pi over 4. So that means that we have a phase shift. We went right pi over 4. So that means C is equal to negative pi over 4. So that's that part of it. Okay, and then to get the B, again, we're going to start with the period here. We are going from 0 to pi over 2. That gets us one cycle here. We can't see the vertical asymptote on that y-axis, but there is one there. So that means the period is equal to pi over 2, and we're going to set that equal to pi over b, which means that b is equal to 2. All right, so that means that our answer here is C. All right, last part here is now we're going to switch to finding exact trig values for tangent. And in order to do that, I think that if we just think through our first quadrant of our unit circle, that'll give us enough information to determine what all these values are. So I'm going to write just that first quadrant here. So I have my pi over 6, which is going to be square root of 3 over 2 and 1/2. And then I have pi over 4, which is square root of 2 over 2, square root of 2 over 2. Those are the coordinates there. And then I have pi over 3, which is going to be 1/2, and square root of 3 over 2. And yeah, I put the 0, 1 on there. Okay, so remember, tangent is equal to y over x. So for these values, what we want to do is we just want to think through. We're going to start in the first quadrant. Where's pi over 6? Well, I see pi over 6 here. This is in quadrant 1, which is nice. We can just see these. So quadrant 1, and we're going to take the y value, which is 1/2, and we're going to divide it by the x value, which is the square root of 3 over 2. When I divide by a fraction, it's the same thing as multiplying by the reciprocal. What I end up with is 1 over the square root of 3. But for these trig kinds of functions, we don't want to leave that radical in the denominator. That's just not like a normal way that someone describes these trig functions. So we're going to rationalize the denominator. If I have a square root of 3 in the denominator and I don't want it to be a radical, I'm going to multiply it by itself. And if I multiply the bottom by square root of 3, I also need to multiply the top by square root of 3. So that gives me square root of 3 over 3. And that is my answer for the tangent of pi over 6. All right, for pi over 4, here I'm sitting at my y is square root of 2 over 2, and my x is square root of 2 over 2. So that is just 1. And again, I'm in first quadrant here. And then pi over 3, I have my y, which is square root of 3 over 2, over my x, which is 1/2. That gives me square root of 3 over 2 times 2 over 1, which just equals square root of 3. Okay, and that was also quadrant 1. All right, so those are nice in our first quadrant. So now we're going to move out of our first quadrant, but these values are all going to be the same, except we're going to be thinking. If I'm in quadrant 2, my x value would be negative and my y value would be positive. If I'm in quadrant 3, both the x and y are negative. And if I'm in quadrant 4, my x is positive and my y is negative. So we just need to think through that and make the values positive or negative. All right, so we want to think 5 pi over 6. So something that's helpful for me, if you're not like thinking through what you memorized about where these are at, I think about this one. 6 pi over 6 is pi, right? So if I went to 6 pi over 6, I'd be sitting where pi is. I'm going just a little bit before that. So this needs to be quadrant 2. And then my x value needs to be negative in quadrant 2. And my y value is positive. So now I'm going to go to my pi over 6 and think through. My y value is 1/2. And that's going to be over my x value, which is negative square root of 3 over 2. So that is equal to 1/2 times negative 2, over square root of 3. Which gives us that negative 1 over square root of 3, which when we rationalize the denominator is negative square root of 3 over 3. I just didn't show all the rationalization. You're going to get this a lot, 1 over the square root of 3. So it's good to just kind of remember it's equal to the square root of 3 over 3. All right. Any questions on that one? Okay, for the next one, we're at 4 pi over 3. So I'm thinking for this one that if I was at 3 pi over 3, I would be at pi. And I'm just going a little bit further than 3 pi over 3. So I'm somewhere down here, which means I'm in quadrant 3. And that means both the y and the x are going to be negative. At pi over 3, my x value is square root of 3 over 2. So that's negative square root of 3 over 2 over negative 1/2. So that's equal to negative square root of 3 over 2 times negative 1/2. Negative times a negative is a positive, and so we end up with just a positive square root of 3. For 7 pi over 4, I'm thinking 8 pi over 4 would take me all the way around to 2 pi, but we're not going quite there. So I'm going to stop short of that 2 pi, and that means I'm in quadrant 4. So here my y is going to